We will now move on to the concept of definite integrals. Now, definite integrals is similar to our usual integration, just that we will have an upper bound and a lower bound. So the number on top is represented as the upper bound, and the lower number is known as the lower bound. Now, to solve definite integral questions, we'll start off with our usual integration. So let's say we integrate fx with our upper bound of b and lower bound of a. We'll get our integrated expression. We'll leave it within the square brackets and put our upper bound and lower bound outside the square brackets. Afterwards, if there are any constants, we will factorize the constant outside of the square bracket. This allows what we have inside the square bracket to be as simplified as possible. So when we sub in our upper bound and lower bound later, it will not be too confusing and we will make less careless mistakes. Now finally, we'll sub in our upper bound first. So sub in x equals to b, subtracted by what we get when we sub in our lower bound. So x equals to a. Then we'll get our final answer. Please note that when we are doing definite integral questions, there will be no more plus c at the end. Now let's take a look at some examples. So firstly, we'll bring up our denominator and we can re-express this as x to the power of negative half. Then afterwards, we'll carry on with our usual integration. So increase the power by 1 and we'll get 3x to the power of half over our new power, which is half. And plus 2x plus x to the power of 4 over 4. Then we will leave this integrated expression within the square brackets, as you can see, and our upper bound and lower bounds outside of the square brackets, so 2 and 1. Then we will simplify the expression within the bracket. Here is where we start subbing in our bounds. You will sub in your upper bound, so x equals to 2 into your integrated expression, and then subtract it by what you get when you sub in your lower bound, so x equals to 1. And then you simplify your answer, and then you arrive at your final answer. Now, if the question requires you to leave it in the exact value, then you will have to leave it in insert form. However, if the question just wants you to have your answer in 3SF, then you can simply key into your calculator and write down your final answer. Now, part 2. Once again, we will start off with our simple integration. So integrating sign will give you negative cosine, and then you need to multiply it by the coefficient of 1 over the coefficient of your x, so 1 over 2. And then you leave it in a square bracket with your bounds on the outside. Then you will factorize out your constant. If you notice, we now have a constant of negative half. So to simplify what we have within the square bracket, we can factorize it outside of the square bracket. Afterwards, we will sub in our upper bound and lower bound. So you get cosine 2 pi over 6 by subbing in x equals to pi over 6, which is our upper bound, and then subtract it by what you get when you sub in x equals to pi over 12, which is our lower bound. And then you simplify it to get cosine pi over 3 minus cosine pi over 6. If the question wants you to leave it in exact form, we have to recall the use of our special angles. Or we can use the method from our calculator to get the exact form. If we key in cosine pi over 3 into our calculator, it just gives us a straight value of half. However, if we key in cosine pi over 6, it will give us a long string of decimals. Afterwards, we can key in answer square and you realize that it gives you 3 over 4. Now you can find back your answer, which is the long string of decimals that we actually want. To do so, we'll square root it on both sides. So our answer will be equals to square root 3 over 4, which will be square root 3 over 2. Now you see that we arrive at our special angle of cosine pi over 6 equals to root 3 over 2. And don't forget that we still have a constant of negative half on the outside, so we need to expand it back to get our final answer. Next, we have properties of definite integrals. When we are solving for definite integral questions, in simpler terms, we are just finding the area under curve, which is done so by splitting the area under the curve into small rectangles. From A to B, there's actually an overestimation of the area under the curve. Because if we notice, the small rectangles are protruding outside of the curve, accounting for extra area that's outside of the curve. From B to C, the area generated will be negative because this is an area under the x-axis, which will give you a negative value. And from C to D, there will be an underestimation as there are gaps between the small rectangles and the actual curve. So there's area that's not been accounted for. Therefore, we can use trapezium or triangles to say that we overestimate or underestimate the area under the curve. Next are the list of properties of definite integrals that students should be able to familiarize themselves with and know when to use it accordingly. Number 1. If the upper and lower bound are the same, then the definite integral will be equals to 0. Number 2. If you flip the upper and lower bound, you need to add a negative sign in front. And vice versa, if you add a negative sign in front of your definite integral, you'll flip the upper and lower bound. Number 3, you can always take out a constant, so your k is your constant, from a definite integral, and it will not affect the constant at all. So you'll just leave it outside. Number 4, if you're integrating two terms, you can always split the terms. So instead of being lumped together in one integral sign, you can split it into two different integral signs following the same bounds. These two properties follow the same properties of your usual integration, so you should be familiar with it already. Now last property, if you want to integrate from A to C, you can split your integrals up from A to B, then B to C. If we represent it in a graph, let's say this is our fx, this point is our A, this point is our C. If we want to find the area under the curve from A to C, we can find it by finding the area under A to B first, and then B to C. And adding the areas up together will give you the same area from A to C. Now let's take a look at a few examples. We are given these two values. If we have to solve for a definite integral with the upper bound of 2 and lower bound of 6, we can simply switch our upper bound and lower bound by adding a negative sign in front. Now this is our second property. So we add a negative sign in front, and then we know that this value has been given in the question, which equals to 4. That's why our answer will just be negative 4. Next, you can see that there's a constant of 5 within the integral, which, according to the property that we know, we can simply bring it outside the integral. Then we know what this is as it's given in our question, so we get our final answer of 5. For the next one, We'll use the property of splitting up our integrals. So we can split up into two different integrals following the same bounds, the same upper bound of 3 and lower bound of 2. This we will know to be equals to 1 from our question, and on the right side, can do our usual integration and sub in our upper bound minus our lower bound. Then we get a final answer of 22/3. Now for the last example, we are required to integrate from 3 to 6. However, the question only gives us the integration of 2 to 6 and 2 to 3. To visualize it, let's put it in a graph. For example, this is our fx, and the question wants us to integrate from 3 to 6. But we have a given value from 2 to 3. This area A will represent the area that we need to find. But our given areas are area B and this entire area, area C. You'll realize that we can find area A by using area C minus area B. This is area C and this is area B, which the values are given in the question. Therefore, it is simply 4 minus 1, which gives us 3.